Thank you, Shirley, and it's a pleasure to be here. I think this intersection of AI and science is very exciting. So that's why I titled my talk, AI for Science, a Revolution in the Making. This is something we are living, breathing, and making it today. And indeed, the last decade has been very exciting for AI. We finally broke through the challenges in scaling up large neural networks. The trinity of AI, which consists of large-scale data sets such as the ImageNet, flexible models such as neural networks and the deep learning frameworks, and the compute infrastructure, especially the NVIDIA GPUs, this combination of data, neural networks, and GPUs made the AI revolution possible. Now, the next phase of this revolution is where we ask how we can make fundamentally impactful discoveries and solve some of the world's greatest problems. And indeed, so much of that lies in scientific applications. And so the question is, how do we harness this AI revolution for scientific advances? Indeed, this is not trivial. A lot of AI that we have designed today, let's say for image processing or natural language processing, for instance, tend to be narrow domain AI, meaning you train on a data set, you test on data that is similar to your training data. But we will see in many scientific applications that's not the case. If you want to discover a new drug, if you want to simulate a new phenomenon that's never seen before, you do not have training data similar to that, right? So what we are really requiring is zero-shot generalization. Zero-shot because you never saw it during training. And this is fundamentally impossible if you just did a standard machine learning technique. What's therefore essential is the domain knowledge. And so this requires close interdisciplinary collaborations. I'll show you several examples of such interdisciplinary collaborations that made this AI for science possible. We need to embed the domain knowledge. We need to embed maybe traditional featureization methods and combine it with data-driven and machine learning models together. And how to make this combination is not a standard recipe, right? So it indeed depends on the application. And that's where I think this is as much a problem in bringing humans together, scientists from many different areas together, setting up a common language and making these collaborations successful as much as it is a scientific problem. So that's where I'm very excited for the future of AI for science. Let me now start with perhaps one of the most pressing problems of our current times, which is the lots of extreme climate events, right? Indeed, the last year was unprecedented. We've all been through this pandemic while also facing extreme climate events. Here in California, the wildfires were almost like it was really dystopian to see that. And I was in Hawaii, and there were lots of floods in Hawaii, of course, the Texas snowstorm. So all these events seem to be getting worse over the last few years, and that's really scary, right? How would the planet look in the next few decades? And to answer that question, what we need are very precise climate models. Can we precisely predict how the global climate change is going to pan out? But unfortunately today, we are still uncertain about these predictions. Indeed, we are all certain that there is climate change and human activity has been responsible for it. But to what extent will we see the warming of the planet? And what levels of carbon dioxide is needed for this warming, that's still unclear. Given this challenging problem, indeed, the question is, can we use machine learning methods to make these predictions precise? And this is a project headed by Andrew Stewart and Tapio Schneider at Caltech called the Climber Project. And they've had extensive experience in looking at bringing together different kinds of simulations and data. And so one aspect they've been looking at is how do we accurately predict cloud cover, because cloud cover is key to rising carbon dioxide levels. But why is this so challenging? Like so many other scientific simulations, this is a highly multi-scale problem, right? Because you have like local clouds, these are small scale events, but how do they all interact together in our global model all across the Earth? And that's what makes it so challenging. And the current methods tend to like combine them in an ad hoc fashion. So what the Climber project is doing is aiming to combine all these simulations with global measurements in a data-driven manner. So what we can ask is, in terms of the next steps here, can we speed up these simulations? Because what it requires is mapping lots of high-resolution simulations, and you want to then map them to global measurements. So how do we do this effectively? And how do we reduce the computational costs of this? So I think this is a great motivation for studying machine learning methods, especially those that can accurately simulate the required processes, such as the clouds here, but at the same time be having high fidelity. So fundamental aspect of such a machine learning based simulation will require what we call operator learning. So meaning you don't want it to limit to a particular discretization. Because what we require in this application is high resolution clouds. So we don't want it to limit to only a low resolution grid and be trained on that and be only working in that scenario. And so what the basis for scientific simulations is a notion of operator, right? Because ultimately you're mapping continuous potentially infinite dimensional spaces and having continuous functions. Whereas standard neural networks depend on the discretization. If you use a convolutional neural network, which is the go-to for image processing, you assume a certain resolution of the image, it's discretized, right? And then you feed it to the network. And the convolutional filters are learned assuming a certain resolution. And on the other hand, if you want to do scientific simulations, we cannot use this framework directly because we want to be able to evaluate at a different grid point, at a different resolution. And that's where we use the Climber project and many other such applications as motivation for coming up with a general framework for operator learning, especially in the context of partial differential equations. Indeed, the world around us is ruled by PDEs. We talked about cloud simulations, all kinds of fluid simulations, whether you want to design an aircraft wing or a car, whether you want to design materials, what kind of strain and stress properties does it have, whether you want to design nuclear fusion reactors. All these are governed by PDEs. And the challenge is they can be extremely complex and expensive to evaluate through brute force, right? Numerical methods will tend to evaluate them on a fine grid because you want high fidelity solutions, and they can be extremely expensive. And that's where a lot of our world supercomputers are harnessed to solving such problems, right? They are the bread and butter for supercomputing. But the question is, can we do better? Can machine learning and AI help us speed up these computations while retaining the fidelity and while being able to evaluate on entirely new instances not seen during training? Because a big issue with standard machine learning is the tendency to overfit to the training data, right? We want it to be able to extrapolate or evaluate on new scenarios, what we call the zero-shot generalization. So that's something to keep in mind, and that's something I'll keep coming back to because that's what will separate this problem and many other scientific problems from standard machine learning approaches. So this is an interdisciplinary project. As I mentioned in the beginning, this close collaboration has been critical for the success of the project. Andrew Stewart with his foundation in partial differential equations and also the knowledge of the Climber project, Kaushik Bhattacharya with expertise in material sciences and properties of materials, all those rich experiences have been critical to coming up with a machine learning method that is robust, that works well according to the metrics that are used in this domain, while also building the flexibility of machine learning approaches. So the way we set out to frame this problem is to learn the solution operator, right? Meaning we should be able to give as input any set of initial conditions, coefficients, boundary conditions, and we should be able to get the solution. That's how the traditional solvers work. So we expect the same from our machine learning-based solver. And so the way we frame this is you're given this set of training data that has inputs as coefficients. So that can be these initial and boundary conditions and the parameters within the partial differential equation family. So we will have a solver for each family, which makes sense because we wanted to learn the structure of that family of equations. For instance, the Navier-Stokes is perhaps the most popular and the most challenging family of equations modeling fluid turbulence. So we will now look at many different initial conditions, boundary conditions, and the corresponding solutions. That'll be our training data. And then we will be asked to evaluate on new conditions, right? On potentially at new resolution and potentially at new grid points. So that's the setup. And indeed, the main aspect is we want to directly learn the solution operator and not just mapping the solution on a fixed grid or a resolution. And this requires a new framework because standard neural networks cannot handle infinite dimensional inputs and outputs, right? They're not designed to do so. So how do we break away from that? So as always, we should start with the simplest case. And with PDEs, the simplest case is the linear PDEs, right? So a subclass of that is the second order elliptic PDE where you have this special structure where, gosh, my cursor just disappears. Never mind, you can see that here. Oh yeah, now it is. So where you see that there are coefficients at each location, and for simplicity, we have the zero boundary condition. You could also have non-zero in general. And so the question is, if we have this framework, we have the inputs, coefficients, the output, the solution. What does it mean to have the solution operator here? What is the structure of the solution operator? So for this class of elliptic PDEs, a lot is known, right? This is indeed the starting point for PDEs. And what's known is the solution has this special structure called the Green's function. And that can be written in terms of an integral operator or convolution. So essentially what you're doing is taking this kappa, the Green's function, and you're convolving it with the value at every location. So indeed, this kernel will be dependent on the input coefficients, and you'll have this continuous convolution operation. So this structure is well known, and this is how you can solve many times in closed form for linear PDEs. But indeed, if I'm talking about Navier-Stokes, if I'm talking about material properties, they're not simply linear PDEs, right? They are highly complicated, nonlinear PDEs. So how do we use this notion of linearity and extend it to general PDEs? So this is where we can use a notion of neural network, which is the compositionality. So in a basic neural network, what you have is essentially a matrix multiplication, and then you have nonlinearity, and you compose several such layers. So each layer is a linear operation, but now composing it with nonlinearity makes the overall system nonlinear. It's not only nonlinear, in fact, it's a universal approximator, meaning you can fit any function into the neural network, any function of a fixed size. So now the same framework can be extended to infinite dimensional functions. And that's where we can use this notion of kernel convolution as a linear layer. And we can compose several such layers to come up with an overall nonlinear estimator of operators. And so that's the basic intuition, that let's stack together many such layers. You can also add this bias term. I'm really sorry, the cursor never appears here for some reason. So you can add the bias term with W here just as an added flexibility. But the main aspect is we're computing kernel convolution in a layer, and then we're adding nonlinearity and composing several such layers. And so this now becomes an approximator for any general PDE, right? And it turns out that this is also done in traditional methods. Iterative solvers tend to stack layers, right? We have like multipole methods, for instance. And so there's also inspiration drawn from that. So you can do the same, but with neural networks, you can learn these parameters, which is the added benefit compared to numerical methods. So that's the basic intuition, that each layer will be this kernel convolution. This is continuous convolution, so it's not dependent on a particular resolution or a grid configuration. And composing it with nonlinearity means we can now capture any general operators, any general solution operators of PDE families. And so the question is, how good is this approximation? So just an additional detail, right? We can also do this composition in a lifted space. You can do like encoding and decoding, similar to what we do in an autoencoder. So you can also do this whole composition in a lifted space. And that's, again, additional flexibility to the model so it can learn a good representation.
Anima, okay, quick question from the audience. I think Jim Simons is said the Laplace operator earlier.
Yeah, so the Laplace equation is a special case, right? So indeed that has this Green's function structure here. But yeah, you could have the more general case with non-zero boundary and so on. Indeed, the Laplace equation has this structure.
Thank you.
Yeah. Yeah, so hopefully this is clear, right? We are taking inspiration from the solution operator of linear PDEs, and then we are composing several such layers with nonlinearity in the hope that we can now capture any general operator, especially solution operators for nonlinear PDEs. And it turns out this is a universal approximator. So for any continuous operator defined on a compact domain, we can use this notion of composition, composing these kernel convolution with nonlinearity to be a universal approximator. So you can see this as a counterpart of a standard neural network being a universal approximator for functions of a fixed dimension. Right now we are extending that to infinite dimensions. So that's nice, right? So what this says is adding this nonlinearity and this composition gives it the flexibility. We can capture any solution operator. But now the next question is, what is the right inductive bias that would make this effective? So just as a fully connected network is not so great for learning on images, we can imagine that if you just did an arbitrary choice for learning the kernel convolution, you'd probably not get such a great result, right? And especially it may not generalize well to different resolutions and grid points. And so that's where we had a series of papers. So as with most scientific endeavors, right, you typically don't just get the result in first shot, right? You have to have this continuous prototyping and trial and error, and also combined with intuitions, combined with some hypothesis. And so we started with graph neural operator and finally proceeded to the Fourier one. So the Fourier one has been the most effective. That's the one I'll talk about. And I think the Fourier one, the reason it's been so effective is because it's a great inductive bias for many of the popular partial differential equation families. For instance, the Navier-Stokes, we know the solution operator is well described in the frequency domain, right? We can talk about what is the frequency representation and its properties. And so that means if we also build this into our neural model, it will be much more effective. And I think that's been a great aspect as well of collaborating with the domain experts, because how are these traditional methods effective? What kind of transforms are they doing? And it turns out, a lot of solvers, this family called the pseudo-spectral family of solvers, they do use the Fourier transform.
Anima, there's a couple of interesting questions that might be short to answer. One is, can you deal with chaotic behavior of nonlinear systems? And then the other one is referring to several slides before, which is whether this iterative convoluted green function representation can be represented in a Feynman path integral context.
So I guess, so regarding the second one, right? So in terms of whether this composition will capture, say, a finite path integral, yes, indeed, because this can approximate any operator, right? A continuous operator on a compact domain. If that's the case, then certainly we can also capture that. So yeah, so it's not just limited to the particular, say, partial differential equation families. There could be other operators where this is also useful. And regarding the first one on the chaotic systems, I have some results. So let's wait until then.
That's great. There's a related question, actually. When David Spergel asked, when you are approximating the Navier-Stokes equation with a neural operator, is the method of first order accurate or second order accurate?
I also have some results for that. So we'll just a few more slides, and then we can come back if it's not at rest. Great, thank you. Thanks, Shirley. And again, keep the questions coming. I like it much more, interactive. If we were all in the same room, right? I think there'd be all the nonverbal cues. So I'd be like, yes, do you have something to ask? But yeah, keep it coming. Awesome. So we have this notion of universal approximation, and like I mentioned, the question was what is the specific neural network architecture now to design? And it turns out that using the Fourier transform turns out to be very effective. The main intuition is because there are global correlations in a lot of these models. So if you think of the Navier-Stokes, the fluid flow, right? You can imagine in the turbulent regime, one part of the flow will, and both in spatiotemporal sense, will have effects on the other part. If you're looking at standard convolutional neural networks, they only have local dependency. So they have small filters. So they cannot possibly capture this global correlation. And also they're great at capturing edges, whereas you don't have these sharp edges, at least in Navier-Stokes, right? So there is a mismatch of inductive bias in that sense between what we've designed for natural images and what's good for scientific applications such as fluid flows. And so Fourier transform is a better inductive bias, and that was our important discovery in making this work. And the other benefit of doing Fourier transform is you have this nice equation, right? So this is signal processing 101. If you recall, the convolution in the spatiotemporal domain becomes multiplication in the Fourier domain, right? So all you need to do is learn this R matrix. So you can now just learn a weighting of your different frequency coefficients and then do the inverse Fourier transform. So the kernel convolution becomes now quick and efficient to do because we have fast FFT routines on GPUs and every possible hardware. This is also resolution and grid independent, right? Because you can evaluate Fourier transform at any resolution. And so this naturally now has the property of being independent of resolution and grid, which is what we require. And so this is great. And so that's the simplicity of this Fourier layer, right? Take the Fourier transform, learn the weighting of that. We additionally regularize to make it sparse. So we select only, I think, the top 20 modes or so, at least for the experiments we've done so far. And that turns out to be also a good regularization because we have nonlinearity to then generate other modes. So we don't need all the frequency spectrum. So think of this as filtering, right? So which can also then learn good features. So it turns out that it's good to add an additional bias term, which captures especially non-periodic boundary conditions. Because the Fourier transform is great at capturing periodicities, right? Because they're made of sinusoids. On the other hand, if you have an aperiodic equation, it's really right. It requires a lot of frequency modes to capture that. In fact, infinite of them. So that's why it's better to have a bias term to capture it in a flexible way. So that's the overall Fourier layer. What we've done is simply use the property of Fourier transform to evaluate the kernel convolution. We've added the bias term, and we compose several layers of that. And in many of our experiments, it's only a few layers that already suffice, right? Just 4 to 5. But indeed, as we scale up our problems and make them more challenging, we can expect even larger networks to appear. So one of the results we are most excited about is the ability to solve Navier-Stokes. This ability to do the solution in the turbulent regime. And you can see it's able to get a high fidelity solution here. So for a range of different initial conditions, we can evaluate this well. But to me, the most exciting part is this is zero-shot generalization. So during training data, we only used low resolution data. So 64 by 64 data, right, in the spatial resolution. And at test time, we directly did super resolution. So we directly evaluated it at 256 by 256 resolution. And so that's the other benefit, that you don't always need this high resolution, expensive training data. Because if you had to gather, I think we had around 1,000 initial conditions. If you had to gather all that at the higher resolution, that would require the traditional solvers, that would be expensive, right? So the benefit of our method is, for training the machine learning based model, we can still do it cheaply, relatively cheaply, compared to those that only work at a fixed resolution. So that's the other benefit, by not limiting to a certain resolution and having this notion of kernel convolution being resolution and grid independent. And indeed, this method is about 1,000 times faster than traditional solvers, because this has fast for Fourier transform operations, a few layers, right? So very efficient to run on GPUs. This experiment, in fact, we just ran on a single GPU, but we can now envision, as the problems get more complicated, we can also scale them up very effectively. So in order to compare with other methods, we trained it and only in a fixed resolution and tested in the same, right? In the sense, other methods cannot generalize to new resolutions. So we evaluated how well it does in the same resolution. And even there, it beats the other method. So the FNO is our approach, and you can see that is the one in the bottom. And so that shows that by aiming for zero-shot super resolution, we can also do better at the same resolution as well, because it's trying to learn the structure of the underlying solution operator, and not just fitting to a solution of a single instance of the problem or single fixed resolution of the problem. I think there are benefits to trying to capture the underlying operator. The other aspect is, how well does it capture the energy spectrum, right? The frequency spectrum. So, because that's how we characterize the solution operator. So just having, say, an L2 error in the spatio-temporal domain may not be enough. And I think that was the earlier question, is this a first order approximation, a second order? How well does it fit the derivatives? So this is where we can be flexible, right? We can train with different loss functions. So when we train with Sobolev norm, the second order Sobolev norm will capture derivatives up to second order. Then we can also capture the higher frequencies more effectively, which is natural. By fitting to higher order derivatives, you're also capturing the higher frequencies well. And so that's what we see here, that it's pretty accurate also in the frequency spectrum. So hopefully that answers that question that was asked earlier. Great. And the question is, once we have this fast method, how can we use it? And one of the common uses of partial differential equation solvers is for inverse problems, right? In so many of the scientific applications, we have an ill-posed problem. Now, if you want to try and image the black hole, if you want to try and understand what's happening underneath the Earth based on surface measurements, they're all ill-posed problems, right? Because there can be many initial conditions that generated your observations. And so given this, having some kind of a posterior mean, variance, and other estimates is the natural thing to do, having a Bayesian solution to it. But we know MCMC is slow, right? You have to sample lots of initial conditions and run the forward solver. And this is where, if we can replace now the traditional method with our Fourier neural operator for forward simulation, we can get a big speed up. So as much as 440x speed up, while getting a similar solution in terms of the posterior mean and other estimates of the problem.
So Anima, we have a few more questions. You just have all the questions coming as you asked.
Yes.
If you don't mind me.
Yes, please.
I waited a little bit. One of the first questions, Xiaohan Jiang asked, can the numerical operator method be applied to high-dimensional PDE scenarios, such as these control problems like Hamilton-Bellman-Jacobi equation? And then there's two questions that are a little bit more related, which is there a way you can, for Miles Kramer, can you remove numerical diffusion from your training data since the model can work with a continuous domain, which in theory might not have any numerical diffusion?
Yeah, those are really interesting. Sorry, I forgot the first question. I was thinking over the second. Can you remind me again?
Yeah, the first question is whether this operator method can be applied to high-dimensional PDE scenario.
Yes. So the answer is indeed yes, right? But of course, how big should your network be will depend on the problem. So the intuition is, you can have the input and output be infinite dimensional spaces. But if we know something about the solution operator being finite dimensional or being low dimensional, then we have more promise for solving that problem, right? If the operator itself is enormous, then you would also require a big neural network. So in that sense, there's no free lunch. So yeah, in terms of the Hamilton-Jacobi or other equations, if there's a latent space where there's a lower dimensional solution, then you can hope for this neural operator to learn that. And that would be more effective compared to just a aspect that doesn't try to look for low dimensional solutions.
Mm-hmm. The second question, if I remind you, is about the numerical diffusion from your training data.
Yeah, so those are good questions in terms of, can we better feed the training data, right, into our framework? So certainly, I think, right now in, many cases, maybe there are existing simulation data available and we can use that, right? But if there is now flexibility to generate on our own, how can we do it more effectively? I think that's certainly possible to do it in a more sophisticated way. Because we could also, think about active learning. Maybe you only want to evaluate at certain points and that's more effective, right? So, or you can, do it both with equations and data, right? Or only equations. So these are all possibilities. Some of them we've started exploring, but certainly we can this is kind of the first step indeed, and there is so many other possibilities.
Yeah, I mean, we have many more questions, but I feel I should let you keep going for a little bit first.
Okay. Awesome.
Thank you.
Thanks, Shirley. Yeah, keep them coming. Yeah, so I think someone asked about the chaotic system. So I guess the most famous and I guess the first chaotic system that was discovered was this KS equation, right? Which essentially is a one-dimensional oscillator. And the idea is this is like the butterfly effect. So you make very small changes in your initial condition, you get an entirely different solution after a certain time period, right? The trajectories can completely diverge. So given this, we cannot expect our neural operators to precisely predict the entire trajectory over a long period of time. And so the question is, what can we predict, right? Is there any hope for chaotic systems? So there indeed is, because for KS equation, for Navier-Stokes, many other popular chaotic systems, there is a lot that has been analyzed and studied in terms of the invariant measure. Even if we cannot predict the exact trajectory into the future, what we can do is come up with certain statistics of what the distribution would look like and what are its properties. And so that's the aspect I think that we can again exploit very well here. Because for KS equation and many other popular equations such as Navier-Stokes, what we have is a Markov property, right? So the solution operator is Markovian, meaning you only need to know the solution at a certain time step to predict the next one. You don't need all of the history, which makes it much simpler, right? So the question is, can we exploit this property now, learning an operator for one time step and then just compose it over a long time horizon? So indeed, over time, we expect this to diverge from the actual trajectory because we are composing just based on one step, right? So we are training based on only one step transitions. We aren't showing it the long-term trajectory to train our neural operator under this new setup. So the question is, how well does it do compared to other models? Possibly models that also have a longer trajectory during their training data, for their training data. So what we see is our Fourier neural operator based on just one step training can predict the trajectory much better compared to the others which diverge much earlier. And indeed, ultimately, all of this diverge over time. But what we see is also that our framework can capture the invariant measures much more effectively compared to the other ones. So this is where there's, again, the benefit of knowing the structure of the chaotic system, using this Markov property and doing this one-step solution here and composing them turns out to capture the invariant measure effectively. This is still ongoing work, so I don't have all the plots here, but we're very excited at this prospect of also capturing the chaotic nature of the systems, even when very accurate prediction of the trajectory itself is infeasible. So that's another aspect that we can do well. And I think even here, it's the resolution independent nature of the Fourier neural operator that works in its favor, because we're not making it dependent on either time or spatial resolution, right? And in this one-dimensional equation, it's just the time resolution. And so it's able to capture the statistics much more effectively compared to the standard neural network models. Great. So moving on to some of the other applications, more challenging applications, plasticity is one such scenario. Don't worry about the exact structure of the equations. Indeed, they look complicated and they are expensive, right? This is multi-scale modeling in order to predict if you're now having a certain force, right, and you want to impinge on, say, this wall, how does this, how does the material deform and what kind of forces can we experience? So this is complex multi-scale modeling. And in this case, we didn't try to model the entire system using Fourier neural operator. And I think this is true in so many scientific applications, right? There are so many pieces to the puzzle. We have modular solutions, there's decades of knowledge built to construct such a pipeline. I don't think it makes sense ever to completely throw all that away and just use a machine learning model, try to capture everything. Unless you're overfitting and doing some narrow domain task, this is bound to fail. So instead, what we did here was to retain the traditional solver at the coarse scale and only replace the solver at the fine scale and use the neural operator there. And so we see that it's still able to capture the properties very well. The question of the stress as a function of the thickness, you can see that it's, we can visualize. We also show it is able to have the same fidelity as the traditional solvers, but be faster, much faster, 5 orders of magnitude faster. And the reason it's so fast is because we have an efficient method in terms of the neural operator, but also because of all the legacy code that's available in a lot of these scientific applications, right? So you can leapfrog from maybe inefficient CPU-based code directly to highly efficient parallelized GPU code. So you're also getting that benefit, right? So this is certainly not an apples to apples comparison, and we are not claiming it to be, but this is a good way for a lot of scientific domains for HPC applications to directly jump onto GPUs and to having all the benefits of efficient neural network implementations. So you're getting that as the added benefit in addition to the efficiency of machine learning models. So we have been now exploring many other applications, and ultrasound is another interesting one where if we can simulate well how the waves would propagate through different objects in our body, right? When we're doing this ultrasound imaging, for instance, with liver versus the blood, you can see there would be difference. And so this ability to simulate this well is important. And again, by working with the domain experts, we've shown that the Fourier neural operator captures a lot of important properties, not just the wavefront, but also the diffraction properties, which is very crucial in that application. And as you will see in a lot of these applications, right, it need not be just the L2 error or some kind of standard error. We want to ask what is important for this domain and work towards our neural operator capturing it, whether to augment the loss function itself or to have other kinds of surrogate measures to ensure that those properties are met. And that's where, again, there is a lot of need for domain expertise here. Yeah, so to wrap up this part of the talk, what you saw was this is a data-driven method. We don't need access to equations, which is another great property. But we are also now working on the scenario where if you only have equations and no data, we can also handle that. That's still work that's ongoing. But I guess the main takeaway here is the ability to do this in a resolution and grid independent manner. The formulation for capturing the operator itself and coming up with a universal approximator for operators. So once we have that flexible framework, it's then building in this inductive bias of the Fourier transform that made it very powerful and effective. So I'm hopeful that there will be many other applications for this, and I'd love for all of you to try this out. The code is available. Reach out to us if you have further thoughts. We'd love to explore other avenues as well. But I'm happy to take now questions on this topic before maybe giving a few snippets of other areas of research in this broad domain of AI for science.
Yes, Anima, we have many questions. Let me go. I will just ask one and then you answer, and then before I go on to this next one, okay? One of them is, how well does this method reproduce known solutions of nonlinear equations such as solitons in the case of Korteweg-de equation? Pardon me for my pronunciation of the equations.
Got it. We haven't tried that equation, right? So as I mentioned, there are vast families of equations, but I guess if the question is how well does it capture, I mentioned like for ultrasound, it was specific to looking at wavefronts and diffraction. We saw with Navier-Stokes, it's the frequency spectrum, how well does it capture? So we can look at different measures depending on the application.
Thank you. And then some of the other audience questions include, were some of the models able to predict the abnormal weather in Texas a few months ago? Do they generally have good predictive ability?
Yeah, so in fact, the storm in Texas was predicted, right? We are pretty good with short-term prediction. So what's still unknown is the long-term climate, that took climate at a global scale. How much is the planet going to warm? There are so many uncertainties. The cloud cover is an important one. So that's where I think it becomes much harder. But we're already pretty good with our short-term predictions.
And some of the audience was wondering what training consists of, in particular when you say zero shot, learning.
So what training?
What training consists of? So I think they were probably wondering, when you have zero shot, means you don't train it for that resolution. What do you give to the network?
Yes. So we are training only at low resolution, right? So it seems magic that we are able to directly do it at high resolution. But the reason is because, we are, even though we've done it at the low resolution, it's trying to solve it through kernel convolution. And so doing that in the frequency domain, it's able to capture the structure of the solution operator better compared to one that wouldn't. So it's the good inductive bias and the framework that makes it possible to directly generalize from low resolution to high resolution data. Like we don't need to change the network parameter. We don't need to do any other change, right? Once the network is trained, we can directly evaluate it at any resolution.
And I'll just give you one more before I let you keep going. Regarding the performance of these Fourier neural operator, can you comment on how important it is to use the correct precision, in the machine precision in a sense, like single, double, or mixed? Does it affect the errors of the results?
Yeah, that's a good point. So I think we only did single, we didn't do double, right? Like in traditional HPC, but also we haven't done the, really super large scale problem set. So I think that's also one that depends on the application. But, I think this could work with right lower precision frameworks because neural networks we know can work very well even in low precision. So we may also be able to do away with very high precision requirements. But that's left to be seen. That's a great question. We haven't fully explored that part of it. So I welcome people to explore that question.
Thank you. I'll leave some for the end.
Great, great. So given that, I think took longer than I expected, let me quickly jump to, oops, I guess, I guess you're no longer seeing the slides. Let me share.
Right, you'll need to share again.
Yes. Yeah. So I wanted to quickly give you another application in AI4Science that's also very exciting in the area of drug discovery or material discovery, right? So drug discovery has been a huge trend over the last year. In fact, the main trending topic in AI was healthcare broadly, and within that, drug discovery was very prominent. So given this, as you can see, this is a slide that I have from NVIDIA Clara, which is a great platform for drug discovery. It has pre-trained models and infrastructure support for all parts of the pipeline. But what I want to focus on today as a scientific problem is the initial part itself, right? How do we search over this vast space of molecules? We've barely touched a small sliver of this space to look for interesting drug properties. So how do we handle the ability to quickly compute properties of molecules, precise computation of the properties, and decide which ones are drug-like and which ones are not for different diseases? And so this is where the collaboration at Caltech with Tom Miller has been very exciting, where what we wanted to do was to capture the quantum chemistry of molecules. So if you do the computation of quantum energy, that's extremely precise. So once you can do those calculations, then you can talk about all properties of the molecule, whether it dissolves, whether it's toxic, whether it binds to certain proteins. So all these aspects you can accurately predict once you can do those quantum chemistry calculations. But the question is, how can we do this? right? The traditional methods, what's known as DFT or density functional theory, is extremely expensive. And so it's really not feasible to do it on large molecules like protein molecules and do it on a large number of those. So what we wanted to do was to use a surrogate machine learning driven model that can replace DFT calculations, but still maintain the high fidelity. So again, what we wanted to aim was zero-shot generalization, right? So in order to predict this for protein molecules, if we required all our training data to be similar sized protein molecules, this would be too expensive, right? We'd spend ages getting our traditional methods to give us this data. But on the other hand, again, we can ask for zero shot generalization. So we will be training only on small molecules, like water, methane, molecules up to, let's say, size 30, right? 30 atoms. And then can we directly use this model on protein-like molecules, which are 10 times or even larger? And so what is the universal property that's transferable from small molecules to large molecules? So it turns out that molecular orbitals have this property. So what you see here in the visualization that's rotating, right, the blobs you see, what it's capturing is the influence of one atom on the other atoms in the molecule. So the main insight is it's not just the neighboring atoms that influence each other when it comes to computing the quantum energy and the forces. You also have potentially long-range correlations in your molecule. And so this insight of using traditional features, which is the molecular orbitals, as the first pre-processing step was really critical for zero-shot generalization. So once we featurized with this molecular orbitals, then we built a graph neural network on top of that. So we use the molecular orbitals to decide the neighborhood for the graph neural network. I'm sure you've probably heard of other graph-based models for capturing molecular properties, but almost all of them only look at neighboring atoms as edges in the graph neural network. And this is really bad because you have long-range dependencies in molecules, especially protein-like molecules, which are very complicated. On the other hand, by using these molecular orbitals, what we are doing is deciding the neighborhood based on the molecular orbital calculations. So now you can have all these non-neighboring atoms as well, right? They can be neighbors in the graph neural network. So you're now learning a much more effective graph embedding in this graph neural network, and you're now exploiting the flexibility of this graph neural network model. So this is, again, a great example of how we can do a hybrid approach. Combine traditional methods like molecular orbitals and with graph neural networks. And once we have this, we can directly predict all kinds of properties of molecules. I've just shown one example here on the free energy of solvation. And what you see is our method, which is the OrbNet, has thousands of times speed up while being accurate in these predictions. And there's also now exciting outcomes for also drug discoveries. Tom Miller has spun this out to a startup called NTOS that he's co-founded, and they're now scaling up and coming up with really large-scale models of OrbNet, which is very exciting. So again, shows the power of using AI while combining deep domain expertise to get the best outcomes. This notion of zero-shot generalization while being very accurate. So I think that's another great example. And what you saw are just two great examples of AI4Science at Caltech. We've launched a campus-wide initiative where we are encouraging these kind of collaborations where domain experts closely work with AI scientists and solve some of the world's most challenging problems. So lots of exciting possibilities here.